Hello, students. These are your notes that will go with homework 14. And in this set of notes, we will be analyzing graphs and looking at linear functions. So we'll do a quick review of function notation and how to substitute in. So I've given you two functions here. The first one is f of x equals 2x minus 1. And the second one is g of x equals x to the second plus 4. So our first problem says to do g of negative 3. So for g of negative 3, you want to be sure that you're using the rule for g. So g of negative 3 equals, and now when you put in your negative 3 as your substitute for x, you want to be sure to use parentheses. And then it says to square that and add 4. So negative 3 times negative 3 is 9. And then we'll do plus 4. And g of negative 3 turns out to be 13. And then our second problem, this is review, f of 5. So we'll use the function for f. And when, again, we make our substitution of 5 for the x, be sure you use a parentheses. So we have 2, then we'll replace the x with a 5. That's our input. And then minus 1. So 2 times 5 is 10, minus 1, and we get 9. So a couple of review problems for us as we begin this lesson and getting you used to function notation. So now we're going to get a little more vocabulary. Today we're going to be looking at linear functions. So a linear function is a function that makes a graph of a straight line. Now, really, all lines are straight, but it seems like we do put that word with it. So makes a straight line. Lines are created when values increase or decrease at a constant rate. And that's going to be important as we look at some data and try to determine whether or not we have a line. So what we'll do in these next 3 examples will be to check if they increase or decrease by equal amounts as we go from one row to the next for both the x and the y. So what we're looking at here, as we go from negative 5 to negative 2, we'll notice that that's an increase of 3. So in other words, negative 5 plus 3 would give us negative 2. So if we're going to have a linear situation, we want to see that our x's and our y's are going up at a constant rate. So negative 2 plus 3 gives us 1. So again, plus 3, and 1 plus 3 gives us 4. So this is a constant rate for our x's. And then we'll take a look at our changes for our y's. So we're going from 7 to 3. So that's a change of negative 4. Then we're going from 3 to 1. Well, that's a change of negative 2. And 1 to 0, that's a change of negative 1. And since our x's remained at a constant rate, but our y's did not, so this is no, it's not a constant rate of change, then this first function is not linear. And that means that if we were to graph this function, it would not graph as a line. So this one is not linear. And that would be the question that we're asked about on this graph or on this set of data. All right, so now we'll look at our second set of data, and we're going to analyze again going from -6 to -3, and so that's up 3. From -3 to 0, that's up 3. From 0 to 3, that's up 3. So this is a constant rate. We'll look at our y's and see if they also go at a constant rate. So 10 to 4, that's down 6. 4 to -2, 4 minus 6 would be -2. And -2 to -8. -2, if we go down 6, we would be at -8. So this also is a constant rate. Since both of them are constant rates of change, then we have a linear function. So this one, if we were to graph it, would make a line. And then we'll look at our third one. Now our data is written in ordered pairs. It's a little harder to see with ordered pairs. So I'm going to rewrite this using an XY table. And so we'll put 2, 5 as our first pair, 4, 8 as our second, 6, 11 as our third, and 8, 14 as our fourth. And we'll start looking at our x's. So we're going up 2, up 2, up 2. So this is constant. And then from 5 to 8, that's up 3, 8 to 11, up 3, 11 to 14, up 3. Both are constant rates. And so therefore, if we were to graph those ordered pairs, we would get a line. We have a linear function. So you'll be looking at the rates of change, and if your x's and your y's both go up at a constant rate, then you have a line. So we'll move on to the bottom of the page and take a look at a graph where we ask some questions about it. So this is different from saying that we have a linear function. This is what we call a line graph. And that means that from one data point to another data point, we do have line segments. But overall, it is not a line. It is what we call a line graph made up of line segments that go from one data point to another data point. So here, this is a section where instead of telling whether or not we have a linear function, we're actually doing the other part of this lesson, which is analyzing graphs. So we're going to analyze this line graph by looking at it and answering some questions. So the first one is, which month had the highest temperature? So we would need to look at our top data point, and that occurs right here. And so what month that is in would be August. So we're going to look and answer some questions. Our second question, B, is which month had the lowest temperature? So we'll look here. Notice that your temperatures are listed over here. We want to know what month had the lowest. We'll find our lowest data point, and that's going to be in February. Now, it doesn't ask us, but let's go back with each one of those and tell what that temperature was. So in February, since I've got it circled right now, it was 29 degrees, and we can pay attention to the unit that is in Celsius temperature. So 29 degrees Celsius. Let's go back to part A, our highest temperature, which happened in August. As we go across and look, that happened where your highest was 33 degrees Celsius. Okay, now we can move on to part C. What is the difference in temperature between February and May? So difference means that we're going to be doing a subtraction. So we want to find May's temperature. So May is at 32 degrees, and we're looking at February, which is at 29 degrees. So I'm going to write those in. February had 29, May had 32. We want to know what the difference is. So 32 minus 29, that difference would be 3 degrees Celsius. So 3 degrees. And then how many months have a temperature of higher than 30 degrees? So we would want to look at our chart and find 30 degrees. So 30 degrees is this line here. And so you have several months. It says how many months have a temperature higher than 30. Now, it doesn't say equal to 30, but it does say higher. So we have, and I'm just going to circle them on here. So we have April, and then May, June, July, August, September, October, November, and December, all at higher than 30 degrees. So if we count that, 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 9 months that have a temperature higher than 30 degrees. And then finally, between which months did a temperature decrease occur? So we're looking at when did the graph start higher than when it finished. Now, it doesn't want the greatest decrease. It just wants to know when there was a decrease. So we'll have to go month to month. Well, if we look, the very first time it happens is actually at the beginning of the year. So we'll probably have a list here. So from January to February, I'm just going to abbreviate this. We have a decrease in temperature. Then we have a climb right here. And then we have a steady temperature and another climb, but we have a decrease happening again. So now we're in August. And so from August to September, there was also a decrease. So August to September. And then we are steady. We have another decrease right here, and this is from October to November. And then it stays steady from November to December. So there you've got your first analysis of a graph, and we'll turn your paper over to do the next section. Continue on with the back side of your notes. I went ahead and split this so that I could have all of it on the screen at once, but that did make the graphs a little bit small. So I wanted to emphasize that the up and down axis on every graph represents the distance from home that's being described in these problems, and the axis going across, or the horizontal axis, represents time. So what we're going to do is look at the different statements and choose the graph that best represents those statements. So the first one is Tom ran from his house to the bus stop and waited. He realized that he had missed the bus, so he walked home. All right, so you have to think about how to read this one. I'm going to go ahead and tell you the answer, and then we will take a look at it. So this is answer G. And so it says that Tom ran from his home. So right here in the corner for G is home. And this is at time 0. So then he ran from his home. That means his distance from home went up as time went on. And then he stopped and waited. Well, while he's stopping and waiting, his distance from home isn't getting any higher. He's not getting any further from home, but it is taking time. And then he realized that he had missed the bus, so he walked home. So again, it's taking time. Walking would be a little bit slower rate, and each step that he takes, he's getting closer back to his distance. So in other words, his distance from home is becoming smaller, and finally he's back at home. He's not far away from home, he is home. So that would be graph G, and so that graph has been used. We won't use that one again. All right, problem number 2, it says opposite Tom's home is a hill. Tom climbed slowly up the hill, walked across the top, and then ran quickly down the other side. All right, so you might anticipate that that one looked like graph G, but actually this is graph D. So again, you have to get used to the fact that that you're looking at that distance from home. So it says Tom's home is, or opposite Tom's home is a hill. Tom slowly climbed up the hill and walked across the top and then ran quickly down the other side. So he's starting here at home and he's walking this whole time. So the whole time that he's walking, he's taking time. So it's going to go across and he's getting further from home. But we have a slow climb. So this slope that we see is a little flat. Then he walked across the top. So that's steady. And then he ran quickly. So that's a faster pace that he's getting further from home. So in all of that story, he's getting further from home. So that distance from home is going up, and it's just his pace that is changing. So you see the different rates of change on those little line segments. So that's answer D. All right, number 3, it says that Tom skateboarded from his house. He gradually built up speed. He slowed down to avoid some rough ground and then speeded up again. All right, so this graph is graph F. So we'll take a look at it. It said, so he's again skateboarding from his house. He's not going back. So we need to choose a graph where he gets further and further away from his house. And he's gradually building up speed. So skateboarding is taking time. Building up speed means that it's a greater slope. It's steeper. And then he slowed down so that speed flattens out. And then he speeded up again. So we have this faster climb, always getting further from the house. So that's graph F. All right, number 4, Tom walked slowly along the road. He stopped to look at his watch, realized he was late, and then started running. This will be graph C. So we'll look at graph C. Again, he's not going back to his house. So we're choosing a graph where he's getting further away from his home. So it says that he walked slowly. So you see this steady pace. He stopped to look at his watch. So that took some time, but he wasn't getting any further away from his house. And then he started running. So you'll see he's getting further away and it's at a steeper rate. So that's graph C. All right, number 5. Tom left his home for a run, but he was unfit and gradually he came to a stop. All right, so that, that will be graph A. So this is graph A. Change colors. Graph A. And we'll look at that. So he left his home, so he's getting further away from his home. So that is an increase, getting further away from his home. But he did gradually come to a stop. So in other words, that distance flattened out. He eventually did not get any further from home than he was before. So up here, we just have a gradual flattening out of that curve. That's graph A. All right, so number 6, Tom walked to the store at the end of his street, bought a newspaper, and then ran all the way back. So now we want to look for a graph where he gets far away from his house and then eventually comes back to it. And so that graph should look a lot like our graph G because he had to go back to his house. That's going to be graph E. So graph E, he walked to the store, so he's getting farther from his house. He bought a newspaper, so that took time, but he wasn't getting any further away from his house. And then he ran, and he's getting back to his house. So he's going back so that he's not far away from his house anymore. And running was a little bit steeper than the walk. So that's graph E. So we just have 4 graphs left. For number 7, says Tom went out for a walk with some friends. He suddenly realized he had left his wallet behind. He ran home to get it and then had to run to catch up with the others. So this is one where he's going to start off getting farther from his house, then going back to the house, and then going far away again. And the only graph left that would do something like that is graph I. So he went out for a walk. So he's getting further from his house at a steady rate, but he has to go home to get his wallet, and it's a run, so a little steeper. And then he is running to catch up with the others. So he's going away from his house again and at a steeper rate. So that's graph I. All right, number 8. It says, this graph is just plain wrong. How can Tom be in 2 places at one time? All right, that is graph H. So let's think about why that's described as being in 2 places at one time. So we see that he's, it looks like, getting further away from his house, and see how this takes time. And I've been trying to keep saying that. But then right here, he's close to his house. So I'm going to put a little black dot. He's close to his house right here. But at the same time, he's far away from his house. So that's what it meant by he's at 2 places at once, and that can't be. So that's graph H. That graph is not a possible graph. Number 9, after the party, Tom walked slowly all the way home. So we have to find a graph that's left. We only have 2 left, where he started far away from home. So if we look, graph J is the only graph where he starts at a distance away from home and it's steady. He walks steadily to where he is at home. So that's graph J. And that means that our final graph, the one that's left, has to be graph B. We'll take a look at it. It says Tom walked steadily to school. He realized that he forgot his wallet, so he turned around. So he's getting farther from home. He turns around, so he's starting to go back toward home. But halfway through, he found his wallet, and so now he's getting further away from home again because he turned around and went back to school. So those are your correct answers. Again, it goes G, D, F, C, A, E, I, H, J, and B. And hopefully listening to those explanations will help you realize how that analysis of the graph worked.